Offset. In order to how many of you understand offset? What is offset in your amplifier? Okay. Any other? So for correct. Okay. So both definitions are correct. So it's just matter of how you explain it. So if you are not giving any input means not giving any differential input. So when you short the two inputs means differential input is 0 and you expect a 0 output. Okay. So 0 output in terms of when you say look at a 0 volt, that corresponds to when you have a plus VDD and minus VDD. But if you have a ground and VDD, then you expect to settle at a mid voltage. Okay, that will correspond to your 0 output in that case. So so when you say 0, it's not an absolute value. 0 means you don't expect anything at it. So whatever, it could be at a common mode voltage, anything, it could be 0 or any DC, okay, depending upon how you provide the supply for your amplifier. So which means if I don't short and I connect them in a unity feedback, so in the unity feedback you expect your output to be same as input, but it won't be same, okay, which means your that will be that is usually called input referred offset. So whatever error you are seeing in the output, that will be divided by your gain and that will appear as a difference in the output, input. So that is your input referred offset. And what does it cause? So let's me just, so if this is, let's say, Vref and I connect it in the unity feedback, so your V out Vref if no offset, okay, but V out equal to Vref plus minus delta V in presence of offset, which I so if I draw a open loop, so you represent it with the source, this could be plus minus VOS, Vref, and this is your again V out. So what will be this? VOS equal to plus minus delta V over whatever gain is here, okay. So that becomes input referred, this is called input referred offset, okay. So sometimes you may not have these direct input accessible, only output is accessible. So in that case you cannot tell how much is the input referred offset, you can only tell what is the error in the output, and that is what we actually require. We are interested in error in the output. But when you design, it is actually the input referred offset which is causing the error in the output, and that input referred offset comes from the mismatch between the two branches of your diff pair, okay. So I will give you an analogy with a simple like daily to daily life what we use. So this is your scale, weighing scale, and let us say you go to market and so we know that usually they have two plates, okay, one for weight, other side you put the object. This is a traditional scale, not the electronic scale which we use these days. If we try to explain in that term, then it's not that simple, but this is simplest. So let's say you buy maybe 1 kg of apple or whatever, and what they do, they put a 1 kg of weight here, okay, and when both sides become balance, that's a 1 kg. But here you go home and you have your own scale and you weigh that, instead of 1 kg it's only 900 gram. There is a 100 gram error. You go back to the shopkeeper and tell, okay, you ask him to remove both the weights and apples. You expect this, but what happened? His scale is doing this. Which means it had error of 100 gram, okay, error or offset. So it might be deliberate or undeliberate, you don't know. Sometimes they deliberately do it, okay, to cheat you, so that they can, instead of giving a 1 kg, they will give you only 900 gram, okay. So what can you do? Now you know, you ask him, okay, you gave me only 900 gram, I asked you for 1 kg, either give me 1 kg or return my money, okay. So you will ask him, okay, you wait again and you do this and keep putting smaller weights. So error, let's say 100 gram, and you put a 100 gram weight here, and then they will now this is balanced out, correct. So now you put 1 kg of weight here again, so the total weight is 1.1 kg, and now you get 100 grams extra apple. Effectively you are getting 1 kg apple, because 100 gram weight, extra weight, has cancelled out your offset. The same concept we apply in the amplifier. So let's see how we do it. So you have your amplifier, you are not putting any weight, which means short these two, connect to Vref, and look whether where output is going. So if it has offset, it will go either high or low, okay. If it's high, which means your positive terminal has more weight compared to negative terminal, and you have a positive offset here, plus Vs. So instead of Vref, that internal op amp terminal will see Vref plus some delta V OS, okay, and it will go high. So if this is VDD and this is ground, this is 0 to VDD. So what I do, if let's say it was 0, then your negative terminal or input has more weight compared to positive. So what you do, you try to introduce, so I know that there is an offset, so which means it has actually offset of Vs, Vref, and this is your actually the, if you look at internally, this is what is happening inside, not this, plus minus, okay. So this is saying Vref, but plus is saying Vref plus VOS, and that is why it is going high. So offset correction. So what we can do, if we know that it has a offset of VOS, then I will introduce the same offset here. Okay, so both input will see the same voltage. That's the whole concept. So how do I introduce the offset on the other terminal? So I know offset is in which direction. Now you try to increase the weight on the other side. Okay. So how can you do that? So we know the diff pair. So you can very well relate this to your that balance actually. So you can call it M1, M2, and this is your I bias, this center. Okay. So which means I have to either change the size of M1 or M2 to increase the weight, or add the current in the output. So if this is my output, and this is my minus, and this is plus, this is minus. Okay. So I know I have a more offset on M1 side, that is what causing your output to go high. I should make M2 stronger. So increase the size of M2. That's the one way you can do. Or I know that this V out is going high, so I can pull some extra current from, let us say I will call it IOS. Okay, and this is a variable current, but how do I know how much I have to add this current, or how much, if I have to increase the size of transistor, how much do I increase? How do you know? How did we figure out in case of balance? Initially you don't know, it's a 100 gram error. Huh? So you have a small, let's say 10 gram, 25 gram, whatever. So you put a, let's say 10 gram or 20 gram, you keep putting that unless direction is changed actually. This side gets heavier than that. So when you put the last bit of this weight and this gets heavier, then you know that whatever the previous weight you added and this, it's lying in between, and if you have a smaller weight you can start putting that, and when it becomes completely balanced out. Okay. So you keep putting the, adding this current IOS unless your high becomes low. That will define, okay, that's where you need to stop. So you do it digitally. This is your IOS. Okay. And if this is my V out, which I know it was high, okay, let us say this is the point where it becomes low, you freeze the IOS here. Okay. So this will cancel out your, and the error in the offset will become will depend what is your bit size or the step you are choosing. Final the step you have, you can get more closer to your desired output or offset equal to close to 0. Okay, what could be the second option? So let's say I don't have weights, I don't have these weights, finer weights, I have only 1 kg and half kg. So I cannot afford to cancel this way. Is there any other way to cancel this? Just think from again from this balance point of view. How can you do that?
Putting that fulcrum.
Yeah, so you can move the center actually. Okay. So second method. So we know the right hand side was heavier. Okay. So which side the center should go? Left or right?
The center should go towards the
Okay. This was your original center. So move the center point. Correct. And you decide where to move when they are balanced out. Correct. So now go back to this. So how can we move the center? Both are at
Leave the bias.
bias current is common, huh? How can you change the bias current? Yeah, size of the transistor or adding a resistor here. This is the technique we most often use, and this is variable. The reason we use this technique, because when we already talked about the placement of M1 M2, you try to match them. Okay, so matching, which means the offset is very small, not that large. So you cannot further break those pieces into a very smaller pieces. There is some limit there. If you make the transistor too small, then that smaller transistor will have larger error actually, because whatever the non-idealities in the process are, they are fixed. If you have a delta L and delta width, whatever the change in length and width, okay, that is fixed, it is absolute change. So when you have a smaller length or width, in terms of percentage, that will be huge actually. So that is why we do not prefer to make the devices too small. So we do not touch the devices M1 M2 when you have laid out in a proper manner. We just use this offset resistor to. So this will effectively this is called actually source degeneration, where you change the GM of your transistor. So it will reduce the GM. So it will make the M2. So it is a positive side, so it should be put here. Usually we put on the in the both direction, because we don't know which one, where is the error in left or right. So depending upon which side the error is, you try to change one of the sides resistor. And so now if these, so if this is ROS 2 and this is ROS 1, so as long as they are same, your center point is at the mid. But when you have a difference in the two, that means it is moving in one of the directions. Okay, and that is what it does actually. And the value of offset is nothing but, so we know that half the current is flowing in both, half of I bias. So whatever value you choose, multiplied by half of the bias current, that will be the offset. And since these currents are in like microamp, and kilo ohm resistor will give you very good accuracy, like you can achieve 1 to 2 millivolt accuracy, even less than 1 millivolt with this. Okay, and by keeping the resistor size still large, order of kilo ohms, because your bias current is very small. Okay, because designing a very low value of resistor order of ohms on chip is not easy. I mean, you use a metal, but kilo ohms of resistor comes from like mostly poly resistors, and if you are using, let us say 10 ohm or something using poly, its size becomes very huge, because width that needs to be very large. but kilo ohm is will take very low area and you can easily do it without any problem.
Can we use different higher order metals like metal, because when you increase the metal layer, the resistance will reduce.
Yeah, resistance will reduce, but we don't prefer, it's order of kilo ohm, that's what I am saying. If you require order of ohms, you do that. Okay, but in this case, you know, your bias current is order of micro amp, so you don't prefer to use metal resistance here, because your area will be bloated. So you should try to use high resistivity sheet resistance, which is mostly the poly actually. You have diffusion resistance also, but those are not very accurate compared to this poly resistor. Okay, metal resistance you use for sensing purpose and all those, but not for general use, general purpose use. Okay, so that is the one way, and you apply the same technique. So what we do, instead of IOS now it will become ROS, ROS1 or ROS2, this guy. So now I am not adding any current here, but I am adding offset resistors and keep increasing one of the resistor depending upon whether your output is high or low, and wait for the output to go low and freeze the code there. So it's done digitally again, and but this is only one time calibration. That's why we call it static offset cancellation. Static offset. So static offset cancellation, and major portion coming from the process and your mismatch due to design and layout. So that is a mainly static parameter. So it will correct most of your offset. It may bring down by 80 or 90%. Still you may have a 10-20% left due to dynamic variations. Dynamic variations means your supply voltage is changing, your temperature is changing. Okay. So with the temperature, so whatever weight you have selected to cancel the offset, that weight may vary with the temperature, or if you have a VDD, that may again cause some variation in the weight. Okay. So in that case you use a dynamic offset cancellation, but for regulator purpose we already know that we don't require ADC kind of accuracy here. So most of the time you don't employ the dynamic offset cancellation, only you live with the static offset cancellation only one time, that's it.